And our agenda is to talk about reaction mechanisms and then to talk about catalysis. So we talked about what a catalyst was. Now we'll talk about how it works, how it does what it does. So let's keep going. Questions, comments, problems at this point? I hope not. If you do, office hours, WebEx, um, come and see me in my office. Give me a call. Send me an email. Something. Let's make sure that we talk. So I want you to tell me the steps it takes for you to get out of bed and get here in the morning. So wherever here is, I assume you leave your house at some point and go somewhere. So for me, that is not just a single step thing. So I don't magically appear at school in the morning directly from my bed. Doesn't happen. There are things that go on in between that. And those things are important. A lot of things I have to do in between the two, even though I would consider all those steps one process, me getting from bed to my job. So I wake up, get out of bed, I get dressed, I get in the car, I stop at the Sphinx to get soda. I get on Ashley Phosphate, I drive to tech, I unload things in my office, I collect my lecture stuff, I go to the lecture room, I unpack it, I set up for lecture. I have written that as a 12-step process because there are 12 things involved. Now, that's not even all of it, but that's the way that I've broken that down. Okay. Now, it's important that we know that we can break these things down into different components. Right? Not everything happens all at once. Okay. And that is important for us to realize. Even though from one standpoint, from one viewpoint, I see it as one process, it's not necessarily actually one process. Okay. Now I could say that an intermediate in this process is getting to my car from the bed, then another from the car to the Sphinx, then another from the Sphinx to Ashley Phosphate, then one from Ashley Phosphate to campus, because it takes forever to get through that part, and then from campus to this building, so the one where I actually teach my classes, which is not that matters. Each thing appears as part of the step, but would not be seen in isolation and not still there once I'm here. So I wouldn't still be on the corner at Ashley Phosphate and Palmetto Commerce trying to make that god awful turn once I get here. So it's no longer observable there. I can't be seen in the Sphinx once I've left the Sphinx. I'm no longer present in my bed once I've left my bed. So even those are things that could have been seen and identified as part of this process, they are not things that can be identified outside of that process. Okay. Now, inevitably, one of those steps is slower than the rest, and that's always the case. And for me, that involves turning onto Ashley Phosphate from Palmetto Commerce. Now, if I go at the right time, things are fine. If I go at the wrong time, it will take me more than 30 minutes, and that is a ridiculous amount of time. And that's dependent on the weight of traffic, and that weight of traffic ultimately determines how long it takes me to get there in the morning. So again, leaving 5 minutes later can be a huge change in what I see. Right? But that's my slow step. And that slow step is the one that determines the rate at which I get to campus. Because that ultimately determines how long it takes to get from my house to campus. And that's the thing. There's always a slow step somewhere. No matter what I'm doing, no matter how I do it, there's always one thing that's a bit longer than everything else, even if it's a tiny microsecond. That is my slow step. And that slow step is rate determining. So those terms are going to be important. Okay. A reaction mechanism is very similar. So very few reactions occur in a single step. Very few. They usually occur as multiple steps from reactant to product. Now, those steps, each one of them is called an elementary step, which, when they're added, make up the overall reaction. Intermediates are species that appear as part of the mechanism, but not a part of the overall final reaction. So, like we talked about in my analogy to me getting to campus, me going to the Sphinx is an intermediate that can be observed and measured, but it's not part of my overall process getting me from my house to campus. So, they're formed, they're consumed in two different elementary steps of the mechanism. Make them here, and I consume them here. So that's the deal. I go into the Sphinx, I come out of the Sphinx. The proposed mechanism must allow us to measure the intermediates formed. Okay. So if I have an intermediate and it is something that can be measured, then that mechanism has to list that as an intermediate. The molecularity of a reaction is the number of molecules in an elementary step. So a bimolecular reaction has 2 molecules that are involved. A termomolecular reaction has 3 that are required in one step, and they're very rare. Okay. Now, we saw potential energy diagrams last time. We saw that we had our energy, the reaction progress, our reactants, and our products. We know that this is the activation energy for that first step. So the difference between the reactant energy and that high transition state. But here we see that that comes down, and then there's this back up. So we go down into a lull, and then we come back. And then there's another EA on that next peak. So that is actually a 2-step process. And I can see that there's an EA for each step. And this well in the middle is an intermediate. That is something that I would be able to measure as part of this process. I can see it, I can measure it, I can get its concentrations. So that's what we're talking about. And that's where you would see that in this graph. So you may see a graph like this that has 1, 2, 3, 5 peaks. And I might ask you, what do you see? What does this represent? And that would be a mechanism. How many steps are in this mechanism? Number of peaks. Which peak has the highest energy? So the biggest EA, that kind of stuff. That's things that you might see with that. Okay, so that's what we can talk about there. Now, come on. Rate laws and elementary steps. Now, I told you at the beginning of this that I could not write a rate law from the stoichiometry of my balanced equation, right? That's what I said. We had to do it experimentally. We had to use that experimental data to do this. Knowing the elementary steps in a mechanism will allow us to determine the rate law. Because what we find is that it's the slow step that determines how fast that reaction goes. And so whatever's involved in that slow step determines our rate. Nothing else does. And that's why some things are not involved. They don't appear there. They have a 0 order. Some things only need 1 thing or 2 things or whatever. So the reaction order for each reactant in the elementary reaction is equal to its stoichiometric coefficient in the chemical equation of that step. So if I have A going to products, that rate is equal to the K times the concentration of A. If I have A plus B going to products, that rate is equal to K times the concentration of A times the concentration of B. These are for elementary steps only. And if I have A plus A going to products, then that rate is equal to K times A squared. Okay, so the stoichiometry there matters. And my rate determining step, well, we cannot tell from an overall reaction what a rate law is. We can determine it from the elementary step that is rate determining. Since we know that overall reactions occur in many elementary steps, the one step that is the slowest determines how fast I make products. And that is called the rate determining step. So again, that's the turn for me from palmetto commerce to Ashley phosphate. Okay, that's awesome. Now, the sum of the elementary steps must give the overall balanced equation. And there can't be anything extraneous in it. So it's only the reactions and the products once we add them all together. The rate determining step should predict the same rate law that is determined experimentally. If it doesn't, then the mechanism that we have proposed is not correct. Okay. That was a lot of gobbledygook. What the hell am I talking about? So let's see. The reaction 2NO plus O2 goes to 2NO2 has 2 steps. NO plus NO goes to N2O2. And then N2O2 plus an O2 goes to 2NO2. That's fine. And one of those is fast. The reaction between the NO and the NO is fast. Reaction between the N2O2 and the O2 is slow. So, what's my rate equation? What's my rate determining step? And what are my intermediates? I'm going to go in the reverse order. So, what are my intermediates? So, what is something that is made in one step and consumed in the next? Well, that'd be this N2O2. So, that's an intermediate. It appears, it gets consumed. It's not part of the overall reaction, but it is part of this mechanistic process. What's the rate determining step? It's the slow one. And what's the rate equation? And remember, I said that if we determine the rate determining step, which is a slow one, the stoichiometry on that will tell me what the rate law looks like. So my rate here is equal to K times N2O2 times 2. And notice that my intermediate is present there. Isn't that fun? I wouldn't have expected that. But that is something that we can see. Okay. And that tells you that there's an intermediate that you're not expecting, planning on, whatever. That's what we're looking at. Do another example. Reaction has the following elementary steps. Br2 plus M goes to Br plus M. That's fast. Br plus H2 goes to HBr plus H. That's slow. And then H plus Br2 goes to HBr plus Br. And that's fast. So my rate determining step is this one here. Are there intermediates? Okay, so is there something that's made which then gets consumed? I don't know yet. And that's because I'm not sure what the overall reaction is. But I know that I get my overall reaction by adding all of these together. So I have Br2 plus an M going to Br plus M. There's a Br over here when I add the next one, so those go away. So I need to add the H2 here, and that gives me an HBr plus H. There should be an H over here, but again, they're both there. And then we have another Br2, so that's 2Br2. So H2 plus 2Br2 plus M goes to Br plus M plus HBr. Okay. And of course, since the M's on both sides, we typically take it out. Okay. Because it's something that's present, needs to be there, but is not part of our overall reaction. Okay. So that means that H2 plus 2Br2 gives me HBr. Yeah, I have two HBr. Oops. So I have one here and one here. So I need to add them together. Hooray! So that makes a lot more sense to me now. And that should be a 2. I need something. I'm that excited. So I see that I have one BR here and one BR here. One M, an HBr, HBr, H, and an H. So when I add all of that happy stuff together, I then end up with BR2. 2BR2, giving me 2BR 2. So I can do this that way. And if I look at charge balance, I have 4 BRs, 2 there, 2 there, H2, 2 H's. So that is balanced. Oh, that's awesome. Oh, that's right. This plus needs to go away because I erased that. Okay, so that's what we're looking at there. I obviously didn't add one when I did it the first time. So sorry, but that's my overall reaction. Okay, the rate equation. Well, rate equation. I'm gonna pull that out. Rate equation here. Rate is going to be equal to K times the concentration of the BR times the H2, because that's what's in my slow step. Okay. Are there intermediates? Yes, there are, because there are things that are made here and consumed there. So that's an intermediate. And we have H being made here and consumed here. I have an H and a BR. And of course, M appears in some way, shape, form is important, but we get it back. We can talk about what that is in just a minute. And my rate determining step is the slope. Now, let's talk about that M. So M is in there, but it's there and then we get it right back. Usually when we have something like that, it's there to make that step different, faster. So that's a catalyst. Our M is probably a catalyst. Okay. And we'll talk about that part a little bit later. Now, experimental data and determining rate laws. So we're looking at the hydrogen peroxide decomposition. The overall reaction is 2H2O2 goes to 2H2O plus an O2. My experimental rate law is equal to K times H2O2 times I minus. Oh God, where did I minus come from? The overall reaction has to take place by more than one elementary step, since I minus is present in the rate law, but not in the overall reaction. So it has to be an intermediate. That means that I2 goes to 2I, and then H2 plus 2I goes to 2HI. I atoms are the intermediates there. Okay, and this should be I minus here. Forgot the charge. I don't know how that happened, but okay, fine. And I know that this is a two-step process. So we go from our H2O2 here to H2 and O2. I have not written that down. It's just species that are there. This step right here is that one. And this step right here is that one. And I see that I have the intermediate in the middle, which is the I. There. Activation energy for both of those listed. And of course, I know that my slow step is the one, H2O2. And the I. Somewhere. I think I may have forgotten something. I'm going to check this slide. If I did make a mistake, I will post a detail or comment for it. I'm really sorry about that. My head is, I can't grasp what it is that I have done. So that's, it's I call it chalkboard fear, but I'm not actually a chalkboard, so I kind of sort of am. But anyway, yeah, I get overwhelmed occasionally. Okay, so let's talk about our practice. That's why I want to label things. So this is my reactant, this is my product, and then this reaction endothermic, because my heat of reaction is positive. So that right there, positive, so that's endothermic. I know that this is my EA for the first step. This is my EA for the second step. I have two transition states, so and we've got this funny symbol for that. I don't even know what it's called. Sadly, I don't know what it's called. It looks almost like it looks something like that. And of course, this is an intermediate here, so that's what we're talking about. Okay, so that's labeling some of the things that I would expect you to be able to look at. I would also know that this is a two-step process with an intermediate formation formed. Now, I cannot tell from this diagram which is the rate determining step. We can't do that from an energy diagram. Okay. Here we have reactant and product already labeled. We have the activation energy for this step labeled there. Activation energy for this step labeled there. This is my intermediate right here. My heat of reaction is right there. And of course, since that goes down, since that is negative, this is an thermic reaction. Okay. So I know this is two steps. I have no idea which one is fast or slow. I know that that's okay. Awesome possum. We'll talk about what those delta G's mean. Like that's our last topic for the semester. Questions, comments, problems on any of that? I hope not. Now, the next thing we're going to talk about is catalysis. I'm going to stop this and recording for us so that we have that last topic. And that is the last of the things for exam 2. Go awesome.